Hey everyone, so it's Mr. Glover here. The topic today is going to be exponential functions. So up until this point, we've talked about what are called polynomial functions, and those are functions that have combinations of different powers of x. So something like y equals x, or y equals x squared, or y equals x squared minus 3x plus 2. Those are polynomials. And we talked about some trends and some things to look for, and eventually we modeled data with these. Today, we're going to talk about a new family of functions called exponentials. So we're going to define what they are, we'll graph a few of them, take a look at them, and then we'll talk about how to model using exponential functions tomorrow. So an exponential function is any function that can be expressed in the form y equals a to the power x, where a is a constant and x is a variable. And then let's talk a bit about what is and is not exponential. So exponential will go on the left, and the right will be things that are non-exponential. So an exponential function, y equals 2 to the x. That's the simplest one. You can also have fractions, so like y equals 1/2 to the x. You can also have other terms like y equals 3 times 0.4 to the power of 7x. That's also exponential. And that comes from the fact that the lower number, call that the base, is a constant, and the exponent is a variable. You might have a constant multiplied by the variable, but your x is in the exponent. Something that's not exponential, y equals x squared. This time your variable is as the base and your constant is in an exponent. So that's a polynomial. You can also have something like y equals x to the x, which is also not exponential. And I actually don't remember what this type of function would be called, but it's definitely going to look different in shape. So let's start off by just graphing the simplest exponential function and taking a look at what happens. So we're just going to plug x values into our function. So this one is going to be like y equals 2 to the minus 2, and you'll get 0.25. And this one's going to be like y equals 2 to the minus 1, which is 0.5. And we keep going. Y equals 2 to the 0, that's going to be 1. Y equals 2 to the 1, is going to be 2. And y equals 2 squared is going to be 4. So now we can plot these points. We'll use the same scale as what we see, so every little check is for every square is going to be worth 1. And we'll get a little bit, it'll get a little messy. We have to estimate half or a quarter, but it should be okay. So we're going to go to minus 2 and 0.25, minus 1 and 0.5, 0 and 1, 1 and 2, and 2 and 4. And so our function takes a shape that looks something like this. And now you're probably thinking that this is going to keep decreasing and eventually it's going to cross over. That's not what happens. And that comes from the fact that you're never going to make something negative by giving it an exponent. It has to be negative first. So this actually doesn't cross the x-axis, and we have what's called an asymptote. And it's not really something you have to focus on a lot in this course, but it's like we've got this imaginary wall here, and the function doesn't cross it. Function doesn't cross this line. All right, so now let's take a look at the domain and the range. If you forget, the domain means all possible x values, and the range means all possible y values. Domain only really changes when you have restrictions on x. So if you've got like a square root, there's no negative inside the square root, so x has to be positive. Or if you've got a fraction, x can't be 0 if it's on the denominator. But for this function, x could be all real numbers, so all real numbers. This is for x. The range affects or is affected by y, and we need to just look at the function, and you can see that the function can't be anything below 0, and it also can't be 0. So y is strictly greater than 0. Exponential functions all have the same basic shape, But and this is not a technical term, but I usually call it the steepness, which isn't really a word, but it describes the situation. The steepness depends on A. For example, 3 to the x, if you plotted it, will maybe look like this, while 5 to the x is going to rise more rapidly, and it will go like that. The larger your base, the faster you will see increases. What about 1/2 to the x? Let's graph this. Let's go to Desmos, let's plot it. Let's see what it looks like. And while we're there, we might as well do -2 to the x. So over to Desmos, y equals 0.5 to the power x. And we get a function like this. This is still exponential, but rather than increasing, rather than going up as we move forward, it goes down as we move forward. That's got to do with the fact that the base is less than 1. Anything below 1, you're going to end up with a decreasing function. And just for fun, let's do -2 to the power x. Oops. If it even graphs the function for us. And we end up with, I don't know if this is plotting properly. No, maybe not. Well, the idea with this is that if x is 0, then you're left with 1. If x is 1, you're left with -2. If x is 2, you're left with +4. And you're going to end up with this kind of spiraling pattern where the function oscillates between positive and negative values. So you go, you have something like 0, so be at 1. At 1, it's going to be at -2. 2, it's going to be at 4. 3, it's going to be at -8, so way down here. This is not exponential. And this function, remember, looks something like this. This is exponential, but it's decreasing. One thing I didn't really point out is that anything to the power 0 is always 1. So regardless of what your base is, if you don't have a number being multiplied out front, you will always have a y-intercept of 1. And you'll see that here, and you'll also see that here. For simplicity's sake, we won't use negative bases. So we're going to have a couple restrictions here. First of all, we're not going to let y be 1 to the x, because that's literally just 1 everywhere. So y can't equal that. And we're also not going to allow 0 to the x, because that's 0. These are both linear functions and don't have the same shape as an exponential. Let's try one more of these. 2 times 1/3 of the x. So this one you're going to have to put in your calculator, and you're going to have to just plug some different values of x into the function to get your y value. So we'll go through the first one. This will be 2 times 1/3 to the -2. And you're going to end up with 18. And next one will be 2 times 1/3 to the -1. You'll be left with 6. 2 times 1/3 to the 0 is just going to be 2. If we keep doing this, 2 times 1/3 to the 1 is 0.67. And 2 times 1/3 to the 2 is 0.22. So what we're seeing is a decreasing function. But it doesn't have a y-intercept of 1, it's got a y-intercept of 2. And that comes from the fact that we've got this number here. That's what's called a vertical stretch, and that's going to stretch the function. So instead of having 1, it doubles it, and it has a y-intercept of 2. So let's plot this. -2 and 18 is going to be way over here, so maybe we'll just start at -1. -1 and 6. 0 and 2, 1 and 0.67, and 2 and 0.22. So we get this rapidly decreasing function that never crosses the x-axis. Doesn't actually curl up. I'm just not very good at drawing lines. It gets closer and closer to 0, but never reaches 0. And it's got this y-intercept of 2. So if we want to fill out what we know, the domain is all real numbers. The range is that y is greater than 0. The x-intercept doesn't exist. There are no x-intercepts because it doesn't cross the x-axis. I don't know what we're supposed to do here. Y-intercept is 2. And the asymptote, remember the asymptote's like the imaginary line that the function doesn't cross. We've got an asymptote on the x-axis. So we've got an asymptote at the line y equals 0. Do you notice anything different about this graph? There's a few things that make this function distinct or different from what we've done. First of all, it's decreasing. It's a decreasing function. It's got a steeper decline, so it's a steeper, we could call it incline or decline. And we also have a y-intercept is not 1. So let's talk about some general trends, some things to look for with exponential functions. So I don't want to have to do table of values every time. When you're given the function y equals a times b to the x, or y equals a b to the x, a will vertically stretch the function. So a is going to make the function steeper. It's like you took the function, grabbed it in 2 spots, and stretched it out like an accordion. Maybe I should focus on highlighting instead of trying to talk. Since the y-intercept of a basic exponential function is always 1, the new intercept will be a, because it's 1 times a. For example, y equals 2 times 2 to the x. I'll have a y-intercept of 2. So now let's estimate some y-intercepts. Verify the following by graphing. So 7 times 1/3 of the x should have a y-intercept of 1. What am I saying? 1 times 7, which is 7. This one should have a y-intercept of 2, or 1 times 2. And this one should have a y-intercept of 0.5. And so we can verify these by graphing. Let's go to Desmos, let's graph them. We'll just make sure. So first function was y equals 7 times 1/3 power x. And it has a y-intercept of 7. So we're good. Second function was y equals 2 times 4 to the power x. And because it's got a larger base, it's increasing, not decreasing, and it's increasing rapidly, so it's steeper. We have a y-intercept of 2, just like we thought. And then the last function, y equals 0.5 times 3 to the power x. Y-intercept of 0.5. And it's sort of increasing somewhere in the middle. So now let's do something a little different. Let's talk about general function. I'm just going to make an arbitrary function, y equals a times b to the power x. And now this is going to say, well, I don't know what a and b are, but I can add a slider. So what I'm going to do is I need to make b something bigger than 0. B is your base. So if you increase that, this is like a base of 1.3, you get a steeper function. If you go up to 100, you get a super steep function. If you lower b to anything below 1, like 0.9, it's decreasing, but it's flat. You can keep going. 0.95, it's even flatter. 0.99 is really flat. Let's keep b at like 2 or 3. A is going to stretch the function vertically. So if I have a function that normally looks like this, I can increase A and it's going to stretch it vertically. As you see, that changes the y-intercept. The y-intercept happens to equal whatever A is. If you make A negative, it'll flip it upside down. So we've kind of looked at general functions. Let's just make some rules. Let's talk about what to look for, what characteristics you'll have. So if the function is increasing, base is greater than 1, you'll end up with a function that looks something like this. If the function has a base between 1 and 0, it will be decreasing. So it'll look like this. The x-intercept doesn't exist unless the function has been shifted up or down, which in this course I don't think you'll find. So for now you can just say it's not going to exist. And the y-intercept is always equal to the coefficient A, because you're going to be stretching the function by that value, which effectively means you multiply your y values by that value. Unless the function's been shifted, which it probably won't do. All right. If you have some time, take a look at example for number 3 on page 445. I've also got some other questions for you to try. I'm not going to make these mandatory questions. This is completely up to you. But if you want to give these a shot, then this will help you understand this unit a little bit more. Hopefully, there's a point where things start to click for you. I think I'll end the video here. I want to keep it fairly short. Hope everybody has a great day. And if you've got any problems, let me know and send me an email. I'll try and respond to them as best as I can. All right, bye for now.